Hey guys, this is the last video in chapter 2, acids in covalent compounds. Just kind of wrapping up what we need to do as far as nomenclature goes. Let's get right to it. So the first thing we have to answer before we even talk about naming or compounds or formulas or whatever is what is an acid? What constitutes an acid? Well, we're going to go with there's several definitions for what an acid really is. There's three of them, the Arrhenius definition, the Bronsted-Lowry definition, and the Lewis acid definition. So for the time being, we're going to stick with the Arrhenius definition, which is a compound that produces hydrogen ions in water. So how does it do that? Well, if we have hydrochloric acid, so HCl here, and we denote it with AQ, meaning aqueous or aqueous, saying that it's in water, what happens is it does something called dissociation. It splits apart and breaks up into its hydrogen ion and chloride ion, two separate ions. And that's not quite the end of the story as far as acids go, but it produces that hydrogen ion. What really happens, though, is that a water molecule picks up that hydrogen ion and becomes a hydronium ion. Kind of proud of this graphic here. That's what happens actually in solution. So sometimes you'll see this H3O plus instead of H plus. That's fine. They mean the same thing. It's just that hydrogen ions picked up by the oxygen of a water molecule. But the point still remains, produces hydrogen ions and is in water, right? Produces hydrogen ions in water. Has to do both of those in order to be considered an acid. Now, how do we name acids? How do we name acids? Well, it's pretty easy. Basically, it's all based on the ion, the anion, because the cation's hydrogen, the anion that's bonded to those hydrogens. So let's take a look at an example in H2SO3, and this is aqueous. So the rules here are if the polyatomic, or if the ion, I guess I shouldn't say polyatomic, if the ion, the anion, call it anion, would end in IDE, so something like sulfide. We'll do an example of that. We'll do H2S. So we lop off the hydrogens, and we're left with an S. S2 minus is sulfide. So the name of the acid starts with hydro and ends in IC. So hydrochloric, and that's one thing that I really try to stress in class, is that the hydro is only for these binary or these acids that don't contain an oxyanion, a polyatomic ion with oxygen. So it's very important that you don't start willy-nilly throwing hydrogen or hydro in there in the names. So in this case, we've got sulfide. So we start with hydro and end in IC. So hydryl sulfuric acid, H2S in water. Okay. If the ion would end in ATE, so let's look at HNO3. Make sure to have the AQ there. If we get rid of the hydrogen, we're left with NO3 minus, and that is nitrate. So we lop off the ATE and change it to IC, and so this would be nitric acid. And finally, if it would end in ITE, we change the name to OUS. So let's do HIO, AQ there. If we lop off the hydrogen here, IO, if we go back and look at our polyatomic ion naming video, IO would be hypoiodite. So we can change the IT ending to OUS, lop this off, change it to IOS, and we have hypoiodous acid. So it's pretty easy. Again, it's all based off of the anion. So if you know your anions, if you know your polyatomic ions, it's not too bad. Let's look at going from the name to the formula. So from the name to the formula, what we have to look at is basically going backwards. So here we've got hydro ending in IC. If we go back and take a look, that came from an ion or an anion that ended in IDE. So this guy instead of cyanic or whatever, it should be cyanide. And that's one of them that you had to remember, and that is Cn minus. Now we're going to tack on hydrogens onto this guy until it's neutral. It's got a 1 minus charge. Hydrogens, we denote them with a positive charge, so we tack those on and we get HCN, right? Positive and negative cancel, and we get AQ. You have to add that AQ there. So this is hydrocyanic acid, HCN. Sulfurous acid. The OUS came from ITE, which means that our anion is sulfite. SO3 carries a negative 2 charge, or 2 minus charge. So that means we're going to need 2 hydrogens, right? A positive and a positive to cancel out that 2 negative. And so what we'll get there is H2SO3, and don't forget the AQ, sulfurous acid. Carbonic acid, IC came from ATE, so this came from carbonate, which is CO3, which has a negative 2 charge. In order for that to be neutral, we need 2 hydrogens tacked on there, and AQ to be in water there. So that is carbonic acid. So it's not too bad, just the same procedure going backwards. And again, as long as you know your polyatomic ions, you're pretty well set. It's kind of important that you remember those. And the last bit of chapter 2 is covalent compounds, which are really easy. Now, we discussed ionic compounds before as a transfer of electrons, right? We're actually giving an electron away. We have a positive and a negative, and they're only held together by their electrostatic interactions. Here, we're actually sharing electrons. The chlorine and the chlorines here are actually sharing this electron pair. And so this electron pair exists around both. So you can think of it, we'll talk about what really happens, but you can think of it as it orbits both nuclei, both of these do. And again, that's for now. But yeah, so that's chlorine, and it's covalent, and they're shared, which, if you think about it, makes it much stronger than an ionic bond. Right, because ionic bonds are only held together, ionic compounds are only held together by their electrostatic interactions. Now, it can be a fairly large interaction. However, for the most part, covalent compounds contain stronger bonds because we have that sharing. If we were to shear that off and break them apart, neither one would have a full octet. Neither one would be very stable. Now, naming covalent compounds, super easy. Because all it is we have a prefix telling how many there are. And we name the first element, then the second element ending in IDE. So we'll start with this middle one. We have 2 nitrogens, so we use di. So this is dinitrogen. And then we've got 3 oxygens, so this is trioxide. Dinitrogen trioxide. Pretty easy, right? Here, we have carbon, but instead of mono, if it's the first element and it's only got one of them, we're just going to put carbon. And if you forget that, think of like carbon monoxide or carbon dioxide, CO2, right? We don't say monocarbon dioxide. So carbon tetra, because there's 4 chlorines, tetrachloride. There we go. Going from the name to the formula is even easier if there was such a thing. Here we're told that there's only 1 sulfur because there's no prefix. And we're told that there's 6 fluorines, so SF6, done. So covalent compounds are really fairly easy. You just have to realize that when they are covalent compounds. So covalent compounds are between non-metals. Now we'll see in the lab, and we'll see a couple other cases where that's not always the case. Sometimes we can have a metal and non-metal, but I don't expect you to know that just yet, know which ones are covalent. So for right now, non-metal to non-metal is covalent, metal to non-metal is ionic. In chapter 8, we'll look at electronegativity, and we'll be able to see which one actually is ionic or covalent. Now, there's a couple things that result from these covalent compounds that you really have to be careful of. So I've got in the next slide a couple of things that students usually miss. Okay. So here are 3 compounds that you might have difficulty naming. This is SO3. Now, you might think at first this is sulfite. SO3 2 minus. But notice we don't have the charge, so it's not an ion. So in this case, it is sulfur trioxide. I get so many people that miss that, say that's sulfite. Don't do that. Same type example here. We've got NO2. Again, you might think this is nitrite, NO2 minus, but it's not. It's nitrogen dioxide. Okay, so don't miss something like that just because it looks like a polyatomic ion. If it doesn't have a charge, it's not. The final thing that trips people up is, remember our definition of an acid has to produce hydrogens and in water, right? This guy is, we just looked at H2S a second ago and we said hydrosulfuric acid, but look, it's a G. Our states are AQ for aqueous in water, liquid, gas, and solid. So this is a gas. And so instead of hydrosulfuric acid, this is hydrogen sulfide. So this is hydrogen sulfide. So this would be more like a multiple choice question where I give you this and say which one is it, and A through D is, you know, hydrosulfuric acid, sulfurous acid, and then none of the above. Well, it's none of the above because it's not in water. So don't miss that. Anyway, so that's it for chapter 2, and hopefully that's it for the first exam. Hopefully we'll have a decent review going by that time, and good luck. And I'll see you guys in chapter 3, where we'll start talking about moles.